Welcome to the lesson on real parametric equations, and we're going to be dealing with a projectile motion. Much of it will be very similar, but it'll be different in that it'll be a parametric equation, right? So let's start with projectile motion right there. So this is drawn x and y. It's a y with respect to x, and this throw that we're going to have goes this way. Right? In the old days, we had the height of the projectile motion that was usually thrown up straight and comes back down. See that in this case, it will go up and down. That's the y motion, isn't it? But what we need to do is that this is the initial velocity with angle theta, like this, right? Now we need to sort of break that down. Let me make it a little bit bigger. That's the initial velocity going this way, and with the angle theta going this way, and this is x of theta, and this is y of theta, guys. Knowing that this is a right triangle, how could you express x theta with respect to initial velocity that's given to us? Yeah? Go ahead. Yeah.
V naught times cosine.
Absolutely. This is v naught times cosine theta, right? So that describes the horizontal motion of this projectile motion, right? How about this right here, guys? About y?
V naught sine theta.
That's right, v naught sine theta. Okay? So we are breaking down this, given the angle and the initial velocity, breaking it down into the x motion, x direction, and the y direction. Yeah? All right. Now, furthermore, continuing this on, guys, we know that the distance traveled is rate times time, isn't it? And the rate that we're talking about is a velocity. And the distance is basically a change in position. If that's the case, guys, this is the way you have to sort of look at things. So the x naught, so x of t is, oops, let me just draw this way. I'm sorry about this. Because I wanted to make it look very similar to the question itself. Now, sometimes there's something called initial height. From here to here is the initial height. Okay, let's talk about this motion one more time. With respect to time, my y direction of the stone goes up and ultimately comes down this way, up and down motion, right? In the x direction, it just goes straight this way. Now, let's look at this over here, guys. So, in this case, the throw could start at 0, or we could start here or here, right? So, we're going to give that a name. It's initial position, right? So, initial position in x coordinate will be x naught plus the rate times time. What is the rate in the x direction, guys? Exactly, right here. So we go initial velocity cosine theta times t. So what this tells you is the initial position, and this right here is the change in position due to the throw. It's a change in position. So far, so good? All right. I'm going to have y of theta right here, semicolon, t, sorry about that. Now, before we could continue, let's talk about dropping something. See this right here, guys? I have this little mini wiffle ball. When I just simply drop this, the distance that this travels is caused by the gravity itself, right? So that could be explained by the expression 1/2 gt squared, right? Because it's going down, right? But there's the initial throw, this version right there, guys, it's going up, right? So it's acting against the gravity. That portion is very similar to this, is V naught sine theta times t. To create a little more room, I'm going to have to erase this part right there. And then it could start at initial position right here, right? Why not? So once again, so this part right here is the initial position in the y direction. This is the change in position caused by gravity. This right here is in change in position caused by the throw, initial velocity. So essentially, this is the equation that we'll be using. And this equation, guys, right here, y of t, is the equation that you have used in the past. Like in Algebra 1 and Algebra 2, the description of the projectile motion was always vertical, up and down motion, right? So the only difference is that we write, instead of Vt, we put V naught sine theta, because we are saying that it could be thrown at an angle. Therefore, the y version of that, the y direction of that, is V naught sine theta. So far, so good? Okay, so that's the intro. So what I want you to do is to work on these 3 questions with your neighbors, guys. Okay? All right, go ahead. Okay, guys, we're back. You had a chance to work with your classmates, right?
Yes.
Okay. So the idea here is to write the next one in terms of the t, and this is y of t. So what are some of the strategies you guys used? Yes, sir.
The x coordinate of the vertex is equal to negative b over 2a of the quadratic.
Got it. So you remember the fact that that is t is equal to negative b over 2a, right? But instead of just memorizing that, let's just think about this for a second, guys. Let's call this t star because the maximum occurs here. So this right there is the y max, right? Occurs right at the axis symmetry. But let's do a quick review. But before we do that, let's say Bugs Bunny's approval rating is 60% plus or minus 2.5%, right? What does that mean, guys? Yeah.
Can be 62.5 or 57.5.
So it's 57.5 all the way to 62.5%, right? But what's the important thing? What's my middle number?
16.
Right. So given that we have ax squared plus bx plus c equal to 0, we know that the x is negative b over 2a plus or minus b squared minus 4ac over 2a. Usually we don't separate the denominator, but I did, right? So what does that tell you? That this must be the middle, and that distance from here to here is this portion right here, right? It's going in either direction, just like this one, right? So when you're thinking about this quadratic formula, it's the left-hand side that's the middle, where the vertex is, okay? So that's like a good intuitive way of remembering this thing. So you could have solved for this. Yeah, I'm going to solve for this anyways, right? T1 and T2. So how do we find T1 and T2, guys? Jamie, go ahead and say it. Yeah, it said y of t is equal to 0 because that's where it hits the ground, right? When it's on the ground, it's no longer traveling. So we want to know when it's no longer traveling to find out when the stone is traveling. Okay? So you could find T1 and T2 using quadratic formula and find the average of the two values, right? But you don't have to. But we're going to need this sooner or later. Okay? For A, though, we know that the y of t max occurs at t star equal to negative b over 2a. All right, I guess then we need to know what y of t is, right? So we need to put that into the calculation. So that's all BGI. What's a BGI, guys? Background information that we should know. All right, so my y of t is, my g is 9.8, meter per second squared. So half of that is negative 4.9 t squared plus initial velocity is 50 times sine of, what is it, 43 degrees times t plus the initial height of 1. So we have that over here. So this right here is equal to negative 55 sine of 43 degrees over twice the a, that's negative 9.8. When you put that in the calculator, that should come out to 3.827541.817. So that's the calculator value that I took directly. But when I'm doing it, I'm going to just use it, substitute the value in the entirety using calculator, right? So to find that y of t star, that indicates that I'll be using the calculator value into this. When you do that, the answer should come out to 72.78 537.416. So you say, therefore, the maximum height is 72.8 meters when time is equal to 3.83 seconds. All right? So that is the correct answer. Now, while I did not ask for specific decimal value, nor did I ask for the time, if I did, you would answer in that particular manner. Sounds good? Now, for part B, how far does the stone travel? One of the common mistakes I have is that people just doubling this number, right? What is the danger of that, guys? That could be a wrong interpretation. Now, if the throw happened with initial height 0, then that length from here to here is, because it's symmetric, will be double that. But in this particular case, from here to here is the same, but my time starts here. So if you double this value, you're going to come to this point right there, not the actual when it hits the ground. Yes, ma'am?
Is t like the seconds it travels or the distance?
Seconds of travels.
Okay.
Time is measured in seconds, right?
Yeah.
Right. Good. So part B, to answer this question, right, I set the y of t is equal to 0, right? When you did that, using quadratic formula, you guys will actually have to show that, right? My t values are, that is negative 0.026567418, and the other value is 7.681651.1051. So this right here is a T1, and this is the T2 that we're talking about, T1 and T2, right? Now, basically, to answer this question, we want to know the distance traveled, right? So the distance traveled is the x of f minus x of I, meaning final x position minus the initial x position, right? Where is my initial position for the x? It's x naught, which happens to be 0, right? What's my final position, guys? X of? How do we denote that? With T2. See, ultimately, it is x of t sub 2 minus 0. So my answer to that turns out to be 308.9902.162. So we say, therefore, the stone 309.0 meters. Are we good so far, guys? All right. Last but not least, okay, for C. For sake of our convenience, I like to actually write the x and t in parametric form. X of t was what, guys? 55 cosine of 43 t, and y of t was what, guys? Right, negative 4.9 t squared plus 55 sine of 43 degrees t plus 1, right? And the question was for us to write a single equation in x and y to describe the path of the stone, right? So basically they want us to convert this parametric equation to an explicit equation, an explicit rectangular equation, right? All right. So what do I do here, guys?
Solve for x of t becomes a t.
Right. Using x of t, we solve for t, which means that the variable x is now 55 cosine of 43 degrees. So with this one, plug into the equations over here. It comes out to the following. Negative 4.9 over 55 cosine of 43 quantity squared x squared plus tangent of 43 degrees times x plus 1. So this behaves like a and a b. So I suppose you could memorize the formula, but it's highly unnecessary as steps are fairly straightforward. Okay guys, welcome back for cycloids. So basically the cycloids that we're talking about is as a circle sort of rolls along. If you choose a point, we want to describe how this moves. Sometimes it's kind of hard to see. So this is moving this way, guys, right? And then it's moving this way. So we need to sort of start measuring the angle here, this way, as a theta. To give you a little more visual of what it's like, is look at the blue dot over here. It's pointing down. That's the starting position, right? But because we're moving along this way, we need to make sure that the angle measurement this way that's the positive. Clockwise is positive, starting at vertically down. Okay, so our reference point is a little bit different. So what it will look like, guys, is follow the arrow, and I will do it this way. It's moving like this, and we'll stop. So that distance that traveled from here to here is what, guys? 1 revolution, right? Which is 2 pi r, but that actually could be more generalized as a r theta, right? As an arc length, right? So let's take a look at the picture, guys. I need to deal with this picture right here, but that one's kind of small, so I'm going to draw on this one. I don't know if you notice this right here, this position right here. So I'm going to approximate the same, and that distance it traveled this much, let's say, right? Arc, and let's say that's the center right here. Let's call this length dA, and then we start measuring from here as a theta. And let's give it some name. Let's call this C as a center. Let's call this P the point. And this is parallel to the horizontal. Let's call this Q. And let's call this point T. Right? But if you look very, very carefully, so hold on. This is the starting point right here, guys. So this excuse me. So this is the starting point, and that's the angle right here. So the distance that this traveled right there is the arc length over here. It's exactly the same, isn't it? And because the angle is a theta and the radius is a, that length from here to here is simply a theta. And that's 0. The origin, O. Okay, so how do I measure the x? Well, x is here, and the y is here. Now, if you sort of think about this thing, guys, okay, without even doing any kind of solving, what is the range of the x of theta? If this is a from here to here, And what is the value of my y theta? In the y value as well, what's my maximum y value, guys? Yeah, exactly, 2a. What's my minimum? 0. So you know this is from between 2a and 0. Now this is slightly trickier, right? So instead of looking at it this way, you gotta sort of be careful how you look at this thing. Okay, so x of theta, what you should be looking at is the center position. As it's moving along the center position, right? It could go what? Either to positive a or negative a. Is that making sense? So let's call this the center position of the C plus or minus a. Okay? So this is sort of what we expect in terms of behavior. Yeah? Okay, now let's try this. What is this right here, guys? The position of the x coordinate based on the angle. Well, if you think about this right here, what is my C? C is this length from here to here. We know it's a theta. That really depends on the what? Angular rotation. So this position is just a theta, comma, the height here is just a. So this constant, isn't it? And then there's this distance right here. This is the x. But what is this distance right here, guys? It's not same as PQ. So that right here and this is the same. So x naught, this position is right here, is nothing more than distance between the origin O and the point T minus PQ, the distance between these 2 points, PQ. And distance between O and T is nothing more than a theta minus the distance between these two is what, guys? You sure it's cosine? Sine, right, because it's the opposite side, right? So distance over here is a sine theta. So we should list it out. X of theta is nothing more than a times theta minus sine theta. Okie dokie? Alright, so what is y theta here, guys? The y is this height, which is nothing more than this minus this height. Do you all see that? Okay, so that would be the distance between T and C, these 2 points, T and C, and y is this, so you subtract this away, so minus the distance between C, Q, and C. So distance for these two is what, guys? Yeah, just exactly A. Minus the distance between these two is what, guys? A cosine theta. Exactly. So y of t, theta, sorry, is nothing more than A times 1 minus cosine theta. So what you need to examine is using this one over here, right? Depending on an angle. When you first start, it's here, isn't it? This point. But that is angle 0. So what is cosine of angle 0, guys? 1. A minus A is 0. Exactly. So y height is 0, isn't it? When it moves 180 degrees like over here, the height should be twice the A, isn't it? So when you put 180 degrees, what do you get? Cosine of 180 is exactly negative 1. When you plug it in, you get 2A. So that seems to match our expectations. So you could go through that argument with these as well. So to conclude, we could express the coordinate of cycloid could be expressed using x theta is equal to A times theta minus cosine theta, and y theta is equal to A times quantity 1 minus cosine theta.